All right, exams are right around the corner, and that means we have got to tackle one of the biggest, most important topics in chemistry, chemical thermodynamics. But don't worry, we're going to break it all down, piece by piece, and turn these complex ideas into something you can really use to ace that test.
So forget just staring at the textbook. In this explainer, we're going to build this chapter from the ground up. By the end, you're not just going to know the formulas. You're going to have a solid, intuitive feel for the material and be totally ready for your exam. Let's get started. I want you to think of this as a climb. We'll start at base camp, just getting the essential language down. Then we'll make our first big ascent through the fundamental laws, learn about the tools chemists actually use to measure energy, and finally, we're going to reach the summit, the ultimate question of why reactions happen at all. Okay, every good climb starts with knowing the terrain. So before we go any further, let's make sure we're all speaking the same language. Let's master the language of thermodynamics.
First up, the system. This sounds fancy, but it's really just whatever we're interested in studying at the moment. It could be the chemicals reacting in a flask, maybe the gas expanding inside a piston, it could even be a single living cell. It's our little corner of the universe that we're putting under the microscope.
So, if that chemical reaction is our system, then everything else, the beaker it's in, the lab bench, you, me, the entire planet, that's all the surroundings. It's a really simple but powerful idea. The system plus the surroundings equals, quite literally, the entire universe. Now for a really key concept, the state function. Imagine you're climbing a mountain. Your altitude at the very peak is a state function, right? It doesn't matter if you took the long, winding path or scrambled straight up the cliff, you're at the same height. In chemistry, things like pressure, volume, and temperature are just like that. They only depend on where the system is, not how it got there. And the flip side of a state function is, you guessed it, a path function. While your final altitude at the summit is fixed, the amount of work you did to get there absolutely depends on the path you took. The winding path is longer. The steep path takes more effort. In thermodynamics, work and heat are our path functions. For them, the journey is everything.
Okay, base camp is officially behind us. We've got the language down. Now it's time for our first major ascent, the first law of thermodynamics. This is all about keeping track of where the energy goes.
Most of the time in chemistry, when we talk about work, we mean pressure-volume work. Just picture a gas expanding and pushing a piston up. That gas, our system, is doing work on its surroundings. And pay close attention to that negative sign in the equation. It is incredibly important, and it all comes down to perspective, as we're about to see.
This, right here, is your secret weapon for exams. Here's the deal. Everything in thermodynamics is from the system's point of view. Think of it like a bank account. Money coming into your account is positive. Money going out is negative. It's the exact same with energy. Heat absorbed by the system, positive. Work done on the system, positive. Any energy leaving the system, negative. Master this, and I promise you, you've mastered half the problems in this chapter.
And here is the law itself. The change in a system's internal energy, which we call delta U, is simply the heat you add to it plus the work you do on it. That's it. It's the ultimate energy accounting principle. Energy cannot be created or destroyed. You can only move it around between heat and work.
Now this is where you're really going to score points on your exam. The first law becomes super powerful when you apply it to specific conditions. For instance, in an isothermal process, the temperature is constant, so any heat you put in has to come out as work. In a perfectly insulated or adiabatic process, no heat gets in or out, so the only way to change the internal energy is to do work. Nailing these special cases is key.
We are climbing steadily. Now it's time to pull out a special piece of gear that chemists use all the time, enthalpy. This is how we talk about energy in a way that's actually practical in a real lab.
So you might be thinking, hang on, why do we even need another energy term? Isn't internal energy, U, good enough? And the answer is just pure convenience. See, it's actually really hard to measure internal energy directly because most chemical reactions don't happen in some sealed, rigid bomb. They happen in a beaker open to the air.
And this is the genius of it. Chemists defined a new quantity, enthalpy, or H, so that the change in enthalpy, delta H, is exactly equal to the heat flow at constant pressure. And since most of our reactions happen at constant atmospheric pressure, delta H is something we can actually measure with a simple thermometer. It's the practical, measurable version of an energy change.
We actually see enthalpy all the time during phase changes. The enthalpy of fusion is just the energy it takes to melt something, like ice turning to water. The enthalpy of vaporization is the energy needed to boil it. And just to give you a sense of scale, it takes about 6 kilojoules of energy just to melt 1 mole of ice.
And here is a fantastic exam tip that also happens to prove that enthalpy is a state function. The energy it takes to go straight from a solid to a gas, that's called sublimation, is exactly the same as the energy it takes to melt it first and then boil it. The total energy change is identical because the start and end points are the same. See, the path doesn't matter.
We've almost made it. We're approaching the summit, and now we face the biggest question of all, the real why of chemistry. What makes a reaction go? Why do some things just happen on their own, while others need a push?
Now, your first instinct might be that it's all about releasing heat. Things roll downhill. It makes sense that reactions would want to go to a lower energy state. But if that were the whole story, an ice cube would never melt on a warm day, because melting actually absorbs heat. It takes energy. So clearly, there's another force at play here.
And that other driving force is called entropy. The simplest way to think about it is as a measure of disorder, or randomness. And the second law of thermodynamics tells us that for any spontaneous process, the total entropy of the universe has to increase. To put it simply, the universe is always getting messier.
So how do we combine these two powerful driving forces, the drive to lower enthalpy and the drive toward higher entropy? We do it with this: the master equation of thermodynamics, Gibbs free energy. The change in Gibbs free energy, delta G, puts enthalpy and entropy into a battle and gives us one single, definitive answer on whether a reaction will be spontaneous.
And the rule could not be simpler. If delta G is negative, the process is spontaneous. And this table, this is your ultimate cheat sheet for any exam. It lays out that battle between enthalpy and entropy. When a reaction both releases heat and gets messier, it's always going to be spontaneous. But when those two forces are in conflict, temperature becomes the tiebreaker. You absolutely positively need to know this table.
So there you have it. We've reached the peak. We can now look at a reaction and predict if it will happen on its own. But here's the catch. Thermodynamics tells us absolutely nothing about how fast it will happen. The conversion of diamond into graphite is a spontaneous process, which means your diamond ring is actively trying to turn into pencil lead. Thankfully for all of us, that reaction is incredibly slow. The question of what controls the rate, well, that's the subject of our next climb.